based startup. He received a PhD in electrical engineering from Drexel University in Philadelphia, Pennsylvania in 2015. His research interests include distributed systems, computer vision, augmented reality, wireless communication, mobile computing, network protocols, software-defined radios, and cellular infrastructure. He will be presenting a talk titled Mapping the World in 3D. Please join me in welcoming back.
Good afternoon, everyone. Thank you for being here today. Thank you for DataCon for having me speak, and for USC for hosting. Very happy to be here and to speak with all of you. So my name is Ryan Measel, part of Fantasmo, and we're based out of Venice. We have 6 people there. We have a team of researchers in Germany as well. So we have a national presence, and what we're focused on is how we represent the world in 3D, how we map in 3D, how applications leverage 3D data, and ultimately how we get to a map of the world. So one thing to frame this talk and what, the starting point before you discuss of how you get there is coming to grips with the fact that the entire world is going to be mapped in 3D, both indoors and out. So we've had an effort from Google and the autonomous car industry for several years now to start mapping the outdoor streets, specifically cities, urban areas. But it's going to go much further than that. We're going to go inside. 87% of the time that we humans spend is spent indoors. And it's one of the least mapped in the world. I mean, our ocean floors are mapped better than the inside of this building right here. And so when we're talking about building a 3D map of the world, that means every centimeter of that world. So the outdoors, the indoors, everything in between. It's very likely that some of you might already have 3D maps made of your homes. This is starting to be a trend in real estate. So if anyone here is familiar with Matterport or some of that technology, it's possible you already have a map of your space, but within a few years, everyone's going to have a map of space. So before we go too much further, let's talk about what a 3D map actually is. So this here is a 3D point cloud reconstruction of the Beverly Hills Hall. I think this is the second floor of the building. 3D maps are essentially describing the physical structure of the space. So from here, we can see this is a world scale accurate map of the building that gives us a sense of the layout, where the walls are, the height of the ceilings, and another layer of information that goes much beyond what the plan is or what you can derive from that. But a 3D map is not just about physical structure, it's also about the semantics of the space as well. So we do care about what is a chair, what is a plant, what is the floor, what is the walls, because ultimately that is what our applications need to have in order to operate inside of these environments. So an overview of what we're going to discuss here today. We're going to talk about why we need this map of the world. We're going to talk about the challenges and opportunities of building this data set and how we can leverage some of those constraints to direct our design. And then we're going to talk about some practical steps of how we actually get there. So starting with the why we need this 3D semantically labeled centimeter level map of the world is because the physical and the digital worlds are converging. There's a new class of applications that are emerging right now that are deeply integrated into the environment, and their application depends on that knowledge of the environment. So these spatial applications, as we'll refer to them, primarily want to answer 2 questions. They want to know, where am I in space? And then they want to know, what is around me? So this comes back to that semantic element of, where are the walls, where are the hallways? How do I navigate this space? How do I interact with this environment? Now, these 2 questions go much deeper than this, and there's a lot of nuance to how these questions get answered. But ultimately, at a high level, this is what needs to be, the information that needs to be provided for these applications to operate. One of the factors that's enabling this, this conversion to happen is that the cost of capture technology is decreasing at an extremely rapid rate. The sensor technology, the mobile devices that's going into autonomous vehicles, is driving a frenzy of hardware and sensor development that is making the cost of acquisition come down tremendously. So for all those that are familiar with the LiDAR that are on top of autonomous vehicles, a few years ago, those would range from $70,000 to $200,000 for a single sensor. Now you can buy them for a couple $1,000s. 2 years from now, you'll probably get them for a couple hundred. It's just going to keep going down. There's already been mobile devices that have time-of-flight sensors in the back of them that you can use to sense depth. And finally, almost everything today has a camera in it. So Amazon is putting cameras in your kitchen, your phones have cameras, your TVs have cameras. 2D imagery is now it's a part of every piece of technology that we touch. What are these applications that need 3D maps? It's a number of existing industries as well as industries that are emerging simply because this data and this technology exists. So we're talking about industries like augmented reality, autonomous robotics, indoor navigation, autonomous vehicles, smart cities, accessibility, emergency response. These are all industries that are going to be completely transformed by the data that they have available to them and can leverage that in ways able to before. This is at a very high level, in a nutshell, of why we need maps. We need it so that these applications to exist, so that our lives can be more efficient, so that our lives can be safer, and that's why it's going to exist. Now, moving from 2D maps to 3D is not an easy task. There is a lot involved in how you create this data, how you leverage this data, how you represent this data, that is a complete departure from historical maps and from 2D maps and the way we think about map data today. And so let's take a look at some of the challenges that exist of moving to this third dimension and how we represent this data. The first point is simply that the world is a very big place. So just the surface area of the Earth alone is around 200 million square miles, which is quite large. Now, today, we might not necessarily care about every centimeter of this, but we certainly care about roads, we certainly care about urban areas, suburban areas, our homes, our businesses, and even these pieces are quite significant in size when we're talking about 3D reconstructions of them. So a reconstruction for a average size mall, something like a multi-tenant retail space that you might be in, is about 20 gigabytes. And that's for one single space. So if you imagine all the buildings on that block, all the buildings in that neighborhood, all the buildings in that city, we're talking about very large quantities of data. And not just a single type of data, but many types of data. So to give you some cost metrics that you can Uber 100 million for streets just to improve the quality of their maps in US and Mexico. So that is just one section of the world, and that's just to start to improve what they want to acquire from this street level data. Somebody like Google that has Street View in all corners of the world, I mean, take a guess at what number they might be paying per year just to upkeep that data set. If there's anyone at Google that wants to share that number with us, by all means, I'm going to guess it's well north of $1 billion. The world is a very dynamic place, so the 3D world changes much faster than the 2D world. There are transient objects, like people, like cars, like animals that are moving around a space all the time. If you just take a 3D snapshot of this room right now, it's going to be significantly different 5 minutes from now as people get up, as people shift. That is not representative of the state that it was 5 minutes ago. So there's these elements that maybe we care about them for certain applications and we want to include those in our map, and for some applications we might want to filter those out. And so semantically detecting what is in our maps becomes vitally important just for the reconstruction step, not only for having those semantics later on. But then there's also things that are what I call semi-permanent features of the space. So if you imagine a conference room that has 10 chairs in it, those 10 chairs will probably stay in that conference room for some amount of time, maybe for a couple years, but never going to be in the exact same, right? Because they're still going to move around inside of that space. And those are elements we absolutely want to represent, because if I have a cleaning robot going into that conference room, it needs to know chairs are supposed to exist in it so that it can alert me if somebody has taken 5 of the chairs out and we have a 10-person meeting coming into that room in the next hour. So these semantics and understanding how a space adapts becomes very important to our ability to map and represent these spaces and for applications to actually leverage that data. There's a lot of different platforms that are going to have to create this data, that are going to have to leverage this data. When we're talking about that laundry list of spatial applications, we're working on things like mobile devices with head-mounted displays, with dash cams, with rovers, with drones, with autonomous vehicles, all these different platforms that have different sensors, that have different operating systems, that have different parameters, that all ultimately want to have the same data layer so that they can do their job. One I'll kind of tease out at this point is that despite how different these, they all use a very similar sensor suite. They all have cameras, they all have inertial sensors, they have depth sensors, and we can exploit that fact to make interoperability possible. Just like we have lots of different inputs, we have lots of different outputs. So there's more than one way that you can slice the 3D pie. There's point cloud reconstructions, there's 3D meshes that can be used in video games and film reproduction or post-productions and various other applications. There's CAD models, so if you want to do civil or architectural work that you require that. There's wireframe models that might be all that's necessary for a robot to operate in a space. They might not need a high detailed texture to navigate, but they certainly want to know where the walls are and how do we represent that in the lowest amount of data possible to make it functional for them. And then there's even the entire 2D layer, because once we start with 3D, we can back up to all the 2D representations too, and it's actually going to be more accurate. We're going to be better producing our 2D data from 3D data than we are trying to make the 2D data in the first place. So we're talking about things like cross sections, elevations, floor plans, structural diagrams, because if anyone here has any experience with architecture or construction, is that the blueprint that you have on the table is never the same as the space is actually built. So when we go back through and map a space and produce a 2D layout from that, that's going to be more accurate than what your blueprint is anyways. There's a tremendous amount of social and legal implications that come into play when you're talking about lifelike 3D reconstructions of reality, not just for outdoor spaces, but for indoor spaces especially. So because of the fact that we're coming primarily from a visual standpoint when we're building these maps, we're using image sensors, we're using depth sensors, we're using things that work in the optical frequencies. It's probably a good starting point to say that a lot of the same laws that are around photography as it stands today will probably be applied to mapping too, right? So this is what we have here is kind of a rundown of the normal operating state for a photographer in an environment. So you're going to be allowed to take photos when you're on public property. When you're on private property that's open to the public, so like USC today, like we could snap a photo in here, that's probably fine. Private property that's not open to public, so perhaps your friend's house, but you have permission to take a photo in there. When you're not going to be allowed is specifically when a private property asks you to leave, right? So it's not strictly illegal. You're not going to get arrested for taking a photo inside of an Apple store, but when their security comes up and asks you to leave the premises, you are obligated to do that by law, right? So you're not going to be able to just walk in anywhere and start making 3D maps. We've tried to do that. We've gotten kicked out. So this is certainly the way things work today. And finally, there's just a reasonable expectation of privacy, right? So you're not going to go in, you're not going to snap photos inside of a bathroom, inside of sensitive situations and things like this. And these are what we have to consider when we're creating 3D maps just as well. And then finally is privacy. The notion of public versus private property becomes a large issue when you are trying to collect this data and store it in a way that makes it accessible for applications. You're going to have to conform to data regulations. So GDPR is just the tip of the iceberg, right? Like people are wising up to how data is used and where it's being stored and what it allows third parties to extract out. So as we start to build up this data set, we're going to have to be mindful of the fact that regulations that exist today and regulations that exist in the future might preclude certain ways of collecting this data and storing this data. And because of that, I think that one of the only ways that you start to get to a space where this is going to work, or a paradigm for privacy that works, is when you have a first-party data hosting solution. So anytime you put this on a third-party server, if Google has a map of your house, right, they can monetize it, they can pull analytics out of it, and you're just never going to be able to be sure that your data is safe. Right? We've all experienced this with recent hacks. Equifax is a perfect example of this, that they scraped all the personal data. What happens when you have a centralized server with a map of all of your businesses, all of your homes, and that gets hacked and wiped? So we've outlined a number of challenges here, but we're engineers, we're developers, and right? So let's look at some of the ways that we need to design to allow us to conform and leverage these constraints to build a system that works in the world. So there's lots of data, right? The world is big. These data files are very large. They're giant binary blobs that can't be easily dropped into a database structure, that aren't easy to link to somebody necessarily. It's going to be extremely cumbersome if you try to channel that all into one space. If you try to bring that into a system where you're sharing bandwidth, you're sharing storage, to even try to do a back of the envelope calculation on how much data it would physically take to represent the entire world, you quickly get to a point where it's untenable to set up your own data center to actually store that. I think even Google at this point might have a very hard time storing that amount of data. So why not distribute the storage? And one of the benefits of this is that when you're talking about spatial applications, most often the request for this data is going to come from within the space that the data represents, right? So if I'm an AR application, or I'm a robot, or I'm an autonomous car, I'm only going to request the data when I'm in space so that I can perform and operate in that space. So what this does is, from a network standpoint, it encourages the data to be pushed all the way to the edge, right? Basically, we want to build a hyper-localized CDN where the data that represents the building sits on in this building, or it sits on the cell tower down the block, right? Like, you want that as close as possible, reduces bandwidth, reduces latency, and makes the data as usable as possible. We have varying platforms that are using the data. We have varying outputs that are coming out. The only way we're going to be able to make sense of all this is if we have standards, right, around how this data is stored, how it is transmitted. And as boring of a topic as standards is, this is how we get to interoperability. This is how a Android device talks to an iOS device, talks to a robot, talks to a headset, is by developing standards that allow them to do that. Private property owners want control of their spaces. So this isn't just for homeowners, or thinking about like, well, I don't want my data out there, but retail owners and business owners are becoming aware of the fact that if I give up my map data to somebody, what can they pull out of that, right? They can pull out my store layout, they can make estimates of my inventory, they could advertise against my space, they could do local product search against my space. And so if Apple is storing that data, or Google is storing that data, they're going to take their platform tax, they're going to cut them out, and they're going to serve the ads on that layer, right? This is a monetizable asset that represents your space, and you should be in control of that and decide how applications get to use that. So first-party data ownership, the only way you're ever going to guarantee this is if you dictate where the data is stored, not a third party. Applications that are utilizing the data want to access this space. They want to access your home. You know, Amazon wants to have their delivery man stock your fridge. What if that's a robot that wants to stock your fridge, right? So like the robot comes, digitally knocks on the door. I want to come in, I want to get a map so I can navigate to your fridge and slide the beer in. The only way this makes sense is if we have robust access controls. And a space owner can say, I want an AR layer to work in this space, or I want a robot to be allowed to work in this space. So when we consider, you know, some of the design principles that we've just developed based on the constraints of the system, we have distributed storage, we have access controls, we have first-party data ownership, and we have standards. What we're really talking about here is a protocol. This is a protocol for spatial data. It's about how data is collected, about how it's transmitted, how it's accessed, and how it's stored. So what I'm proposing is a decentralized spatial protocol where we're making up the stack of pieces specifically tailored to handling this data and serving this data. First of which, and most importantly, location DNS. So just like or a geo, yeah, I want to walk onto this block and say, you know, I'm standing here in the US quad. What buildings are around me? What data can I access? So I'm going to ask my server and say, here's my GPS coordinates. I want a 100-meter radius of all the buildings in this area that have data that I might be able to utilize. The next step is the distributed storage layer. So once I've figured out to say, okay, there's 3 buildings on this block that I'm able to access data from because I'm a robot and I'm going to make my deliveries, I now need to access the maps for those. So the DNS is going to tell us where that data is stored, and me as an application can go and make a request from that server to then pull that data down. And the final aspect here is standards, so that when I know I'm making a request or when I'm contributing data, that I'm doing so in a way that promotes interoperability. So we'll dive into each of these a little more specifically. First of which, this location maps, where the operation property owners, so if I see this building, that I could come in, I could register the geospatial of this building and all the buildings that I have onto this DNS. And once I do that, I now am able to set the resolvers of the data. So when somebody's coming to me to make a request, DNS will tell it, here's where you need to go get the data from, and here's the access permissions. So if I'm an AR app, I need to check to say, am I even allowed to request the 3D map of this space so I can operate? This is basically robots.com. If you're crawling the web and you go to a website and they say, okay, here's what you're allowed to do on my website, here's what you're not, this is exactly what this provides, but in a spatial sense. So am I allowed to pull data from this space if I'm a certain type of application? And what this enables is, again, we prescribed any single place where this data needs to live, the owner gets that where the data lives, and robust access. Distributed storage. Resolvers that are serving the data can store that data anywhere. So they could put it on their own hardware. They could put it in their own cloud instance. This gives a completely abstracted layer. We've seen this start to happen in several of the blockchain communities are doing this exact same thing, where it doesn't matter where my data is stored as long as I have an interface to access that data and a resolver that can also the of this access. Just like a robots.txt on a web page, a crawler could ignore it if it really wanted to, right? It shouldn't, but it could. In our case, we really can't have people accessing data, right? So if I say like a AR application is not allowed to access my home, then it's not enough to just say that it can't access my home. Somebody actually has to enforce it. So that is the resolver. And by virtue of the fact that I as the owner of the space, am setting the resolver, I have trust in the resolver that it's going to respect the access permissions that I'm putting on that space. So when that request comes in, the resolver can check the permissions and say, okay, you can or you cannot have this data. And this again facilitates this hyper-localized CDN because we can have those resolvers acting as trusted sources on any of the data that they represent. And it supports the first-party data ownership model as the owner's complete control of who the resolver is, and that in effect gives them control to prevent their space from being used in ways that they don't want it to. Finally, standards. There's a number of existing standards that can already be leveraged for this sort of data. So there's already standard organizations that do work with geospatial data about the ways it can be transmitted, streamed, processed, stored. So there's already a large swath of existing standards that we can leverage to build this network, but there's a few that are going to emerge simply because of the nature of these new spatial applications. I've listed a couple of these that are going to have to emerge here. The first is a camera positioning standard. So going back to that initial question of where am I if I'm a spatial application, that is precise localization. So we're talking centimeter level accuracy with position and orientation inside of a space. The only way we can do this is by having a map of visual features. So this is a machine readable visual map. If anyone's seen Google's visual positioning system, this is an open source version of that. This is how you would share data from a mobile device or a robot and then come back later and say, here's what I'm seeing. What is my position relative to the spatial versioning format? When I've already come in and on a day-to-day basis, on an hourly basis, and I want to keep up because the utility of my map is only as useful as the correctness of my map. So what I need to do is continually update it. But to do a full scan, if you can imagine going back and having to do a full scan of that mall, and it's 20 gigabytes every single day, very quickly you're going to build up a ton of data, right? But if we can just detect what the differences are in those data sets, all we need to do is store the diff. So this is just like a versioning system for code or documents, right? Like we don't have to store the whole document, we're just going to store the sentence that changed. So the spatial versioning format is a 3D data format that allows you environment in a very sufficient way. Finally, 3D semantic JSON. There's plenty of ways that you can mark up 2D data. There are very few ways that are robust enough and expressive enough to mark up 3D data. And so if I just want to make a request and say, what types of assets are in this room? Are there chairs? Are there tables? You know, are there plants? Are there paintings? I don't necessarily want to have to, as an application, pull down a huge file, parse through that, and figure that out for myself. If I just have a semantic markup that I can pull down, that is much more efficient and much more expressive to perform those queries. And what this enables is a network effect of sensors. So if we have these standards and phones and robots are all able to operate in the same space and share this data, then they can all update each other, right? So we don't have to come in and map once for iOS, map once for Android, once for ROS. We can just map a single time, and they can all share in that data, and then we get this huge proliferation effect where they're all talking and sharing data together. So to bring this to a high-level overview of what this looks like is that you have spatial applications that are talking to a distributed peer network. That peer network is in charge of being the resolver and serving the queries on our location DNS. So the location DNS can be stored in a blockchain similar to any of the smart contract systems that exist today. Blockchain is what property owners can go in and specify what spaces they own, what the access controls on that are, and what the resolvers are. And then finally, the peer network then connects out to this abstracted distributed storage model, and that's where the actual data is stored. So data and these other pieces are much too large to actually store into any sort of blockchain type system. What all the blockchain does is it allows us to have distributed control of where that data is stored and how it's accessed. So we've talked a lot about how this system should be designed and how this should come together, but it's frankly not possible without core technology to enable it. So this is primarily what my company Fantasmo has focused on since our genesis, is how do you create reliable and accurate reality captures of spaces? How do you localize devices inside of those spaces? And then how do you provide semantics and tooling that allows humans to annotate and edit that data in a meaningful way? So these are some examples of different reality capture technologies. One of the things we talked about being the different types of input that you have from all of these platforms, be it cameras, LiDARs, 360 cameras, inertial sensors. The goal here is to be able to reconstruct from any of those sensors such that they can all work and update each other. So here's a couple examples of some of the different capture types that we have. The top left here is Abbot Kinney in Venice, and this was from a 360 camera, just an off-the-shelf Garmin 360 camera that was attached to a bird scooter. So just riding down the street, capturing 360 imagery, and we now have 360 photospheres in addition to a world-scale reconstruction. On the right is a street by the beach in Venice. We do a lot in Venice because that's where our office is. This is taken with just a phone. So taking a normal iOS device, walking up and down the sidewalk, collecting 2D images, and reconstructing those 2D images into a 3D world-scale representation of that street. These two down here at the bottom are reconstructions that were built from Velodyne LiDARs. So these are the same LiDARs that you find in vehicles, and simply on a platform that enables them to just be carried by a human. So we just simply walked into these spaces, carried the LiDARs around, also 6 camera that we use to semantically filter and also colorize the data. And so this sort of data, which is much more high density because all of the LiDARs that are being used, can be captured as fast as you can move through the space. So this here on the left is the Beverly Hills City Hall again, and on the right is a local warehouse facility. These were captured in a matter of minutes, just the amount of time it takes to walk down the hallway. Camera positioning, this is the core piece to answering that where am I question for spatial applications. This is a very brief example of what that looks like, because this is a machine task to take a query and try to position itself in 3D space based on that query. So what we have here on the right is a visualization of a localization map. Some people refer to it as SLAM maps. It has a few different names, but there are visual features inside of that map which can be compared to the query image, and we can find places or features in the query image that line up to that map, through which we can perform geometry and figure out what our precise position orientation is relative to that. And finally is tooling. For 3D data, GIS systems that have historically worked with LiDARs and imagery in this way are extremely cumbersome. They want you to be bought into their whole platform. They have steep curves. They're just not approachable for an average user. Like how does your grandma use a 3D map, right? She's not going to go into into Esri or Arc or one of these programs and load up spatial layers. Just going to open it on a browser, right? So it's about making this data easily viewable and accessible and editable from tools that we're already familiar with. So this screenshot here is an example of rendering a 30-byte point cloud inside of a browser, which this can be done on a normal laptop, even mobile devices. So to bring this back around, and what I want to press as the points of this talk and where we're headed is going to be mapped in 3D. The technology is already there. It's already being deployed in a number of ways, but we have a fragmented market. There was 50 companies mapping the streets of San Francisco as recently as the fall. We're doing a lot of duplicate work to build these maps, right? But it is happening, and it's going to happen with greater frequency and move into the spaces that we spend most of our time in. There's a number of challenges of working with this data, collecting this data, and serving this data, and those challenges can primarily be addressed through a decentralized spatial protocol, which is going to provide distributed storage, standards, first-party data ownership, and robust access controls. Finally, it's the core tech that makes it possible. So if you don't have the ability to leverage the data, build this into reconstructions, and make it accessible for applications, then none of this is going to happen. Which brings me to the end. My name is Ryan. You can reach me at Fantasmo. Our company website is fantasmo.io. And if you're interested in camera positioning, we have an open standards group from camerapositioning.io where we work on developing that standard together with augmented reality and robotics developers. And at this time, I'd be happy to take any questions.
What about integration of existing 3D mapping information like architectural drawings and things that might already exist rather than having to go back in and remap?
Sure. So the question was, what about leveraging the information we have about 3D space already, such as architectural drawings? This is actually a way that many companies are already operating. So you need floor plans, 3D maps, they'll build them from those or floor plans or cat malls that already exist. Accurate. It's just never built as the right. So if you want maps, you have to go start with 3D to even bring that in. But certainly we can build semantics from those maps as well. So you might imagine in a department store that you could label the sections of the map based on the drawing or what they planned out for that map to be. Yeah.
Can you kind of talk about how you're dealing with these large point clouds and how is there like a database that you're using so that you can query these data points and do instances and things like that?
Mm-hmm. Yeah. So the raw data we often just store as binary blobs. So we do use Postgres because of its great geospatial extensions to do queries and to find which of our blobs we want to work with. But the data itself is much too large to actually put into a traditional database structure. So all of it is URI references to just where that data happens to be stored. Now the data itself, we do have a number of specific data structures that we store that data in so that we can make queries against that data set. So one very common data structure that's used for 3D data is octrees, where the entire cloud is broken up into octets recursively down. And that makes it very efficient to find sections, to do replacements, to do matching and merging. And there's a number of other, yeah, exactly, KD tree lookups, R trees, just a number of different data structures that are very efficient for performing a lot of the processing that we do. Mm-hmm. Yeah.
Postgres, do they implement that kind of
Other thoughts? Yeah. Yeah. Mm-hmm. Yeah, so the question is, when we're thinking about first-party data, are we also considering proof of location so that somebody can't spoof the GPS or the positioning data that they're using to access? That's a great question. I think that's one of the enabling technologies that's going to bring this all together. That's not something that we're particularly working on right now. There actually are a few other companies who are specifically going after that proof of location goal. And I think those systems are perfect couplings for providing access management to a system like this, where if I can use a proof of location system to verify my position, then I can be confident that I'm going to pass over data. So in the instance of I'm a robot, I'm in the space, I want to prove that I'm in the space before you're going to give me the data, right? Yeah. One? Okay.
Last question.
Yeah.
So because your capturing devices is the quality vary a lot from a form to those high-end line things, and then so how will you? And then in the end, you might be put those data together as little pieces, and how do you handle those data, the variety of the data input?
Yeah. So the question is, how do we handle the disparity of inputs that are coming in and the quality of data, and how do we merge that together? We use a variety of techniques depending on the data type. So if it's imagery, we're looking at visual features and using that to align data sets. At the end of the day, all of our reconstructions come back to world scale. So we can use rigid transformations in a 3D space to perform that registration between data sets. So even if I have a low density sparse data set, I can match that against a high density data set just by doing a 3D registration.
So Brian, thank you so much. That was a very good session.
Thank you. Oh, thank you so much.